Okay. So, we will take another example, then we will move to the inductors, right. So, this is another example. The voltage pulse distributed by the following equation is impressed across the terminals of a 0.5 microfarad, right. So, and it is given V t is equal to 0 volt for t less than equal to 0. It is you make less than 0, less than, right. So, and it is 40 volt for in t in between 0 and 1 second, and your 4 into e to the power minus t minus 1 volt when t is greater than 1, but I mean in between 1 and infinity, right. So, let me clear it. So, you have to find out few things. You have to first is V t is 0 volt for some time t less than I have told take t less than 0, and 40 volt when t is greater than 0 less than 1, and 4 e to the power minus t minus 1 for t greater than 1 less than infinity. So, you have to find out, derive the expression for the capacitor current, power and energy. This is the first thing. Sketch the energy as function of time, then specify the interval of time when energy is being stored in the capacitor, and specify the interval of time when the energy is being delivered by the capacitor, and evaluate the integrals 0 to 1 p dt, p is power, and 1 to infinity p dt, and comment on their your significance, right. So, we know I mean very simple it is. Look, we know from equation 5 that I is equal to C into dV by dt. C is given 0.5 microfarad, that is 0.5 into 10 to the minus 6 farad. Hence, expression for the capacitor current is given as, I mean just for each interval you apply C into dV by dt, right. So, first case voltage was 0. So, C into your dV by dt 0. So, it is 0 for t less than 0, and then in second case in between 0 and 1 V t is equal to 40. So, if you take the derivative with respect to t, it will be 4 and multiplied by C. So, it will be 2 microampere, because 10 to the power minus 6 is here, that is t greater than 0 less than 1, and third one it was given 4, here it was given 4 into e to the power minus t minus 1. You take the derivative of it, C into dV by dt, and if you do so it will be 0.5, that is into 10 to the power minus 6, that is C value in farad, into minus 4 e to the power minus t minus 1. So, it is minus 2 e to the power minus t minus 1, that is microampere for t greater than 1 less than infinity. So, expression of power from equation 8, we know that power is equal to V into I, right. So, this is your V into I, not marking here, it is understandable, V into I. So, V is 0 for t less than 0. So, it will be 0 watt, and then V is equal to 40, right, and I is equal to 2 microampere, or what you call 2 microampere, here it is written for t greater than 0 less than 1. So, multiplied by 2 it will be 80 microwatt, right, it is microwatt. And another one similarly, the last one you will get 4 into e to the power minus t minus 1 into, that is your V t, right, into that current minus 2 into the power minus t minus 1 is if you just multiply, it will be minus 8 into e to the power minus 2 t minus 1, right. So, this is microwatt for t greater than 1 less than infinity. This is the power. Now, energy expression as follows, that directly you will get from your what you call equation 10, right. So, you know half C V square energy is equal to. So, first one is V is 0. So, it is 0. Second case your V was given your 40, right. So, just simplify, C is equal to 0.5 into 10 to the power minus 6 farad. So, half C V square, simplify, you will get 40 square microjoule, when your this is your, it will be less than somewhere is equal to, it has gone, right. So, I am correcting it. So, and third case half C V square, it will become 4 into e to the power minus 2 minus 2 into t minus 1 microjoule. These are all micro, just you do it, please do it. I have done it for you, simple thing, right. So, this is your what you call energy expression. Now, just let me clear it. So, figure 7 shows the plot of energy function, right. So, one is 4t square microjoule. So, it looks, its first part will be up to 0 to 1. So, it looks like a parabola, right, and then 4 into e to the power minus 2 into t minus 1 microjoule. So, it is exponentially decay. So, this side is W in terms of microjoule, and this time this time is your x axis is your time second. So, if you plot it, it is 4t square up to this, and then that your what you call that your other part in between t greater than 1 less than infinity. So, this is your 4 e to the power, this part 4 e to the power minus 2 into t minus 1. This part is 4t square, and this part is 4 into to the power minus 2 into your t minus 1, right. So, this is your energy plot, function plot. Now, energy, second thing is that energy is being stored in the capacitor whenever the power is positive. That means, when power is positive, that energy is being stored. So, if you come to the power expression P, that 8t microwatt, so it is positive, that means energy is being stored, and when power is negative, when t greater than 1 less than infinity, it is negative, that means power is being delivered. So, here that your energy is being stored in the capacitor whenever the power is positive, hence energy is being stored in the interval 0 to 1 second, right, and energy is being delivered by the capacitor whenever the power is negative. Thus, energy is being delivered for all t greater than 1, right, second. So, now next is the integration of p dt. So, it is the energy associated with the time interval corresponding to the limits on the integral, right. So, thus the first integral represents the energy stored in the capacitor, because if you look into that, it is given 0 to 1 p dt, that is your in between that p is positive, right. So, it is given your p dt, and p is equal to v into I, right. Your earlier we have given that p is equal to v into I. So, it is 80 your microwatt. So, here if you see that it is energy being stored, right. So, whenever in the second integral represent the energy returned or delivered by the capacitor in the interval 1 second to infinity. So, when 0 to 1 p dt, it is 0 to 1 8t dt. So, you integrate, right, it is definite integral, you will get 4 microjoule, and 1 to infinity when you make, it is 1 to infinity, and in that case minus 8 e to the power minus 2 into t minus 1. Integrate and simplify, you will get minus 4 microjoule. So, energy stored is equal to energy delivered. So, it is matching, right. So, the voltage applied to the capacitor returns to 0 as time increases without your limit. So, the energy returned by this ideal capacitor must equal the energy stored, right. So, this is what we take this example for our understanding, right. So, next we will take the inductors, right. So, after that we will move to your first order circuit. So, inductors. So, an inductor, just look into that. An inductor is an electrical component, right, that opposes any change in electrical current. Little bit you know from your higher secondary physics. So, it is composed of a coil of wire wound around your supporting core, that is this figure, this is figure 18, right, whose material may be magnetic or non-magnetic. So, this is coil wound and this is the core material. So, let me clear it. So, this is your figure 8, right. The behavior of inductor is based on phenomena associated with magnetic fields. So, the source of the magnetic field is your what you call charge in motion, that is current dq by dt, or current charge in motion, that is I is equal to dq by dt, or current, right. If the current is varying with time, that you know, then the magnetic field is varying with time, right. So, a time varying magnetic field induces a voltage in any conductor linked by the field, this you know. The circuit parameter of inductance relates the induced voltage to the current, this you know. In general, you know that V is equal to L into di by dt, we will come to that, right. So, let me clear it. So, if the current is allowed to pass through an inductor, it is found that the voltage across the inductor is directly proportional to the time rate of change of the current. So, by using the passive sign convention, right, V is equal to L into di by dt. So, this is equation 20, where L is constant of proportionality called inductance, this you know, right. The unit of inductance is Henry and inductance is the property, right. So, that your inductance actually is the property whereby an inductor exhibits opposition to the change of current flowing through it measured in henries, right. So, this is actually your what you call little bit of your many things you know, this is a simple thing, but just to start this introduction. So, little bit I wrote for you, right. So, let me clear it. So, the circuit symbols for inductors as shown in figure 9 have following passive sign convention. This one this is the sign of inductor when it is air core. Here it is written figure A, air core. When this symbol is there, it is iron core. Here it is written, it is iron core. And when this variable sign is there, that arrow is there, this is variable iron core. So, this is your symbols of the your what you call the inductor, your what you call inductors, right. So, it is when you write like this, it is air core. When you make 2 bar, then it is iron core, and if it is a variable iron core, then 2 bar and then make arrow, right. So, this is the symbol of the inductor. So, let me clear it. So, equation 20, that is V is equal to L into di by dt, right. That is the voltage current relationship for an inductor. So, this figure 20 shows the relationship graphically for an inductor whose inductance is independent of the current. Like capacitor also, we saw I is equal to C into dV by dt. Such an inductor is known as linear inductor, right. When inductor is independent, that L is independent of the current, then this side is V, y axis, x axis is di by dt, and is simply straight line passing through the origin, and this is the slope, that L is the slope is actually in this case inductor. So, the L is not a function of I current, right. So, it is then it is linear inductor, right. So, this is the voltage current relationship, simple it is. Now, if V is equal to L into di by dt, that means we can write that di is equal to 1 upon L V dt. This is equation 21. Now, if you integrate, then I should be is equal to 1 upon L, then minus infinity to t V dt dt, right. V is a function of t, say. This is equation 22. So, if you integrate, same like as capacitor, same philosophy, that it will be 1 upon L t 0 to t V t dt plus I t 0, that is equation 23, where I t 0, like capacitor also we explain something, same philosophy. It is total current for in between minus infinity, t greater than minus infinity, less than t 0, and I minus infinity is always we will take 0, right. So, the idea of making I minus infinity 0 is the practical and reasonable, because there must be a time in the past when there was no current in the inductor. So, it is past only, past history. So, in some time there was no current in the inductor, right. So, it is very practical of this kind of assumption. So, I minus infinity we take it as a 0, right, and the power delivered to the inductor will be P is equal to V into I, right. So, V is equal to L into di by dt into I. So, this is equation 24. The energy stored is that W is equal to minus infinity to t P dt, that is minus infinity to t L into di by dt into I, right. And if you integrate this one, then it will basically it will be L minus infinity to t I di. So, that is half L I square t minus half L I square minus infinity, that is your I minus infinity square, right. This is equation 25, but just we have seen that I minus infinity is equal to 0, right. Since it is 0, I minus infinity, therefore, energy stored is equal to half L I square. This is equation 26, it is a simple thing, right. So, equation 20, that means this equation 20 is your following important properties of an inductor can be noted. Like capacitor also we saw some property, so same way we will see for inductor, that is V is equal to L, equation 20 is V is equal to L into di by dt. So, it can be noted from equation 20 that when the current is constant, because V is equal to L into di by dt, if I is constant, then di by dt is equal to 0, right. Therefore, the voltage across an inductor is 0, thus an inductor acts like a short circuit to DC, right. So, when we will solve numerical steady state condition, we have to assume that inductor acts like a short circuit to DC. Second one is the current through inductor cannot change instantaneously. So, your in this case, according to equation 20, that is V is equal to L into di by dt, a discontinuous change in the current through an inductor requires an infinite voltage, which is physically not possible. Thus, an inductor opposes an abrupt change in the current through it. For example, the current through an inductor may take the form shown in figure 21a, I will come to that, whereas inductor current cannot take the form shown in figure 21b in real life situation due to your discontinuities. That means, this kind of change for inductor in figure A it is okay, but here abrupt change suddenly it is directly suddenly from here it is falling to 0, it is not possible in real life, right. So, this kind of discontinuity is not possible, right. So, this is given current through inductor, this is allowed, right, but this kind of thing not allowed, right, and abrupt change is not possible in the inductor, right. However, the voltage across an inductor can change abruptly. Next one is, an ideal inductor does not dissipate energy, right. The energy stored in the inductor can be retrieved at a later time. It is same philosophy like capacitor, whatever we have just seen before. The inductor takes power from the circuit when storing energy and delivers power to the circuit when returning your previously stored energy, right. So, a practical and non-ideal inductor has a significant resistive component. It has a significant resistive component due to your fact that the inductor is made of a your what you call conducting material such as copper, which has some resistance and also has a winding capacitance due to the your capacitive coupling between the conducting coils. That means, it has resistance, also some capacitance is there, right. So, and it is that your what you call exact circuit for an inductor, right, practical inductor, but generally Rw is the resistance of that coil, inductor coil, and Cw is that your capacitance thing between that your coupling capacitance between that your what you call two windings, say, because so many windings are there. So, this is called cup Cw, is called coupling capacitor. So, this is the exact circuit for the inductor, but in reality Rw is very negligible and Cw also negligible. So, we only consider inductor, resistance we generally not consider. For some problem we also consider to find out the resistance and inductance of the inductor, that we will see later, and Cw generally we do not consider for our as far as our circuit analysis is concerned. So, in figure 22 that I told you, Rw is called winding resistance and capacitance Cw is called the winding capacitance, right. So, the presence of Rw makes it both an energy storage device, because resistance your resistance is there, and an energy dissipation device, right, because inductor can store energy, it can be dissipated in the form of heat, say in the resistor, since Rw and Cw are very small and hence they can be ignored, right, in most of the cases. So, we will ignore that. Next is series and parallel inductors, right. So, this is a simple circuit that your 23 shows a series combination of n inductors, where voltage V is there, L1, L2, L3 all are up to Ln, all are connected in series, current flowing through this is I, voltage across L1 is V1, across L2 is V2, like this, across Ln in Vn, right. So, this is series connection of n inductors. So, you apply KVL, then you write V is equal to V1 plus V2 up to Vn, sum it up, this is equation 27. Then or V is equal to L1 into di by dt plus L2 into d2 by dt, di by dt plus L3 di by dt and so on up to Ln di by dt, right. You take L1, L2, L3 all common, so it will be into di by dt, right. So, or V is equal to Leq di by dt, this is equation 28, where Leq is equal to L1 plus L2 plus L3 up to Ln, equation 29, right. Therefore, equation 24 shows the equivalents are equivalent for the series inductor. It is like a resistor, this for inductor case it is like a resistor in series, when R1, R2, R3 all resistance are in series, you add it, so you do the same thing for inductor also, just to add it, right. So, this is an equivalent circuit and this is Leq, Leq is equal to L1 plus L2 plus L3 and so on, all the inductors you add. So, equivalent circuit for the series inductor. So, inductors in series are combined in exactly the same way as resistors in series, right. So, now consider your parallel connection of n inductors as shown in figure 25. The inductors have the same voltage across them. So, this is the voltage and this L1, L2, L3 up to Ln, all inductors are connected in parallel, and this is the current entering into I, right, and then I1, I2, I3 all current going to inductor 1, inductor 2 like this. Therefore, Kirchhoff, if you apply your KCL, right, then I is equal to I 1 plus I 2 up to I n, right. If you make it, I is equal to I 1 plus I 2 plus I 3 up to I n, right, and we know that I 1 is equal to 1 upon L 1 T 0 to T V dt plus I 1 T 0, that is initial inductor current, all like capacitor, whatever we do it, same thing, plus 1 upon L 2 T 0 to T V dt plus I 2 T 0 and up to your what you call 1 upon ln T 0 to T V dt plus I n T 0. Now, collect all the terms of your what you call multiplied by integration T 0 to V dt, it is 1 upon L 1 plus 1 upon L 2 plus up to plus up to plus 1 upon ln into T 0 to T V dt plus I 1 T 0 plus I 2 T 0 plus your up to I n T 0, or you can write I is equal to 1 upon L eq T 0 to T V dt plus I T 0, whereas 1 upon L eq is equal to 1 upon L 1 plus 1 upon L 2 plus 1 upon L 3 plus up to 1 upon L. It is same as that your resistance are in parallel, when 1 upon R eq is equal to 1 upon R 1 plus 1 upon R 2 like this, same as the resistor, and that and initial thing I T 0 is equal to I 1 T 0 plus I 2 T 0 up to I n T 0. This is equation 31 and this is equation 32, right. So, inductors in parallel are combined in the same way as the resistors in parallel. Next, we will take 2-3 examples. So, just look into this. The current through a 0.01 Henry inductor is I t is equal to 5 t to the power minus 10 t ampere. Determine the voltage across the inductor and the energy stored in it. Since we know that V is equal to L into di by dt and L is given 0.01 Henry and I t is given 5 t, your what you call into e to the power minus 10 t, it is given. So, V is equal to your what you call L into d dt of I. So, if you do if you take the derivative of it, it will become 0.05 e to the power minus 10 t plus 0.05 t into minus 10 into e to the power minus 10 t. If you simplify, it will be V is equal to 0.05 into 1 minus 10 t into e to the power minus 10 t volts. So, energy stored is half L I square. So, half L into this is your I square, right. So, 25 t square into the power minus 20 t. So, it is basically 0.125 t square e to the power minus 20 t joule, right. So, this is a simple example. Next one is find the current through a 5 millihenry inductor if the voltage across it is V t is equal to 30 t square for t greater than 0 and it is 0 for t less than 0. This is given, right. So, also determine the energy stored within 0 t greater than 0 less than 0.5 second. This is also asked to do it. So, you know that I is equal to 1 upon L T 0 to T V t dt plus I t 0, right. So, given that L is equal to 5 millihenry, so it is 5 into 10 to the power minus 3 Henry and I is equal to 1 upon your L, that is 5 into 10 to the power minus 3 0 to t third V is equal to 30 V t is equal to 30 t square given dt plus 0, that is your I t 0 is equal to actually 0, right, because anything that V t is given and find the current your 5 milliampere if the voltage across it, because V t is 0 for t less than 0, right. So, your in this case your I t 0 is equal to 0. So, it is 2000 t cube ampere. So, the power P is equal to V I, V is equal to 30 t square into 2000 t cube, it is 6 into 10 to the power 4 into t to the power 5, right, and the energy stored is then given by it has been asked in between 0 and 0.5. So, integrate this 0 to 0.5 p dt, p is equal to 6 into 10 to the power 4 into t to the power 5. So, you substitute here and integrate, you will get your omega is equal to 156.25 joule, right. A simple example. Now, another one is that figure 26 shows a simple circuit under DC conditions. Determine I, Vc, Vl and the energy stored in the your what you call in the capacitor. So, you have to, this is a simple circuit is given, this is and you have to find out under DC condition, you have to find out I, Vc, Vl, right. This is I and this is Vc and this is your what you call and the and your Vl, right, and the energy stored in the capacitor and inductor. This we have to find out. So, question is that under DC condition, right, under DC condition we replace the capacitor with an open circuit. For DC just we have seen for capacitor, and for DC condition inductor should be short circuit. So, it is short circuit, inductor is short circuit. That means, this 3 ampere, this no current is flowing to 3 ampere because it is open circuit, right, no current is flowing. So, then what will be I? It is 4 plus 1 5 ohm and 10 volt. So, it will be 10 by 5. So, 2 ampere. So, I is equal to, and same current, this is a simple series circuit then, right, nothing is flowing here. So, I and IL, this it is same, right. So, I is equal to IL is equal to 10 upon 4 plus 1 is equal to 2 ampere, and Vc is equal to voltage across the capacitor is actually your this one, this is your voltage Vc, this is your voltage Vc, no current is flowing here. So, basically this is actually, I can write in better way, this is actually Vc, and it is your what you call this this current I your IL is flowing to this. So, Vc is equal to 1 into IL, right, and IL is equal to 2 ampere, therefore, Vc is equal to basically 2 volt, right. So, let me clear it. So, that's why Vc is equal to 2 volt. Now, energy your what you call energy stored in the capacitor is Wc is equal to half C Vc square. So, we have got your half C is given 0.1 into 10 to the power minus 6 farad, because 0.1 microfarad. So, converted to farad into Vc is equal to 2 volts, so 2 square joule, so 0.2 microjoule, right, and that in the inductor will be your half LIL square. So, it will be half into 0.2 into 10 to the power minus 3 into 2 square. So, WL is equal to 0.4 millijoule, right. So, this is your what you call that your energy stored in that inductor, right. So, next is this problem, another problem. So, simple problem, it is simple problem. So, in figure this, that your in this figure, that this figure IT is given 2 minus e to the power minus 10 t milliampere. If initial condition of IT 0 is given minus 1 milliampere, find initial conditions I1 0, then VT, then V1 t, then V2 t, then I1 t and I2 t, all you have to find it out, right. So, this is the circuit is given, this is the circuit is given, and 2 inductors are there in parallel, right. So, and these 2 inductors are in parallel means that this inductor and this inductor, these are parallel, means their equivalent inductance will be 4 into 12 divided by 4 plus 12, right. So, it will be your say 3 Henry, right, and then 2 Henry is in series. If you find out your same like a resistor, inductor case whatever series parallel combination you have done for resistor, for inductor case it is same, right, and then this 2 Henry is there. So, 2 plus this 3, so equivalent your thing will be 5 Henry equivalent in inductance, right. So, let me clear it. So, in this case the circuit given that IT is equal to 2 minus e to the power minus 10 t milliampere, and I2 0 is given minus 1 milliampere, it is given. Now, at t is equal to 0, you find out at t is equal to 0, you put here in this expression at t is equal to 0, right. So, in that case you will get I 0 is equal to 2 minus 1, so 1 milliampere. Therefore, if you apply here your KCL in the at this node, right. So, for initial condition you can write that I 0 is equal to I 1 0 plus I 2 0, right. So, then as one of them is given, and I 0 also we have computed. So, other one easily you can get it. So, let me clear it. So, then I 0 is 1, we have got it, and I 2 0 is given minus 1 ampere. Therefore, I 1 0, the initial condition, that is to your initial current, that is 2 milliampere, right. The LEQ I told you that we just I just show you how to calculation. It will be 2 plus 4 into 12 upon 4 plus 12, it will be 5 Henry, just I showed you. Therefore, Vt is equal to, that means this is the circuit. So, this is your V. So, Vt is equal to, I mean if you draw the equivalent circuit, so this is actually your V, V is equal to say Vt plus minus, and this is actually your 5 Henry, right, and this is the current say I, right. So, that is why, and this is actually your Leq is equal to this 5 Henry, right. So, let me clear it. So, Vt is equal to Leq di by dt. So, Leq is 5 and I is equal to 2 minus e to the power minus 10 t millivolt. So, if you just take the derivative, it will become Vt is equal to 50 e to the power minus 10 t millivolt, right. Now, therefore, V1t will be 2 into di by dt, right. If I mean if you your what you call this is to your Henry and voltage across is V1. So, it will be 2 into that is your L into di by dt. So, here it will be your V is equal to your 2 into di by dt. If you I you know this is given. So, it is 20 e to the power minus 10 t millivolt. Now, since V is equal to V1 plus V2, right, therefore, I mean this one your this is the voltage V2, that means this is actually voltage V2, right, that is voltage across this and across this it is V2. Therefore, if you apply KVL, so it will be V is equal to V1 plus V2, right. Therefore, let me clear it. Therefore, your V2 is equal to V2t is equal to Vt minus V1t. Vt we have computed earlier 50 into e to the power minus 10 t and V1t minus 20 e to the power minus 10 t is equal to 30 e to the power minus 10 t millivolt, right. And I1t will be is equal to 1 upon 4 0 to t V2 dt plus I1 0. So, 30 by 4, right, and your then 0 to t e to the power minus 10 t dt and I1 0 is equal to 2, right. If you just simplify, integrate and simplify, you will get I1 I1t is equal to 2.75 minus 0.75 e to the power minus 10 t milliampere. You please simplify. Similarly, for I2t 1 upon 12 0 to t V2 dt plus I2 0. So, it will be 30 by 12 0 to t e to the power minus 10 t. You put here V2t is equal to, right, plus your I2 0 is given, you know it is minus 1, and then you integrate and simplify. You will get I2t is equal to minus of 0.75 plus 0.25 e to the power minus 10 t milliampere. This is I2t. So, with this capacitor inductors topic is closed. 1 and 2 example is given here, like example 1 you will solve it for that. So, this is that you read it, I am not reading, everything is given here, right. So, and answer is also given, this is the answer is given, right. So, only one problem here I am giving here, and this is the answer and this is your problem, right. Thank you very much, we will be back again.